Can you guys hear me okay in the back? I'm trying this speaker gizmo thing. Awesome, thank you. To give another test of that, can I get hands for who in here are undergraduate students? All right, and hands for graduate students. Oh wow, pretty good mix here. All right, so given that I'm a graduate student, I thought we'd start off with a short guide to graduate school. This is actually primarily taken from Matt Might. It's going to lead somewhere. This actually has a purpose, possibly just to break some ice here. Okay, so we're going to start off with a circle. It's going to represent all of human knowledge. And when you get through high school, you gather some knowledge. And you go through college, you gather some more knowledge, and then you start specializing a little bit. This is your computer science, AI, whatever sort of nub here. And then you start working towards a master's degree, and you take more classes, and you get a little more knowledge going. And you start reading research papers, and you're all the way out here to the edge of human knowledge. And you're like, I want to know more about this. So you think you're going to go on towards a PhD maybe, and so you start zooming in. And you're right there, and you start working for a few years. And eventually, the boundary to human knowledge gives way, and this becomes your thesis. Except you've been working at this for a few years, and this is what the world looks like to you. It's what you've done and what the edge is. But of course, to your friends, to your family, to every other person in the world, this is what the world looks like. And you're that little dimple out in the end. So given that our world here is AI, this is the AI lab. Thanks for having me here. We're going to start off this talk talking about AI, because that's the center of the world. And I'll talk a little bit about where cognitive architecture fits into all this. And then we'll get to one particular cognitive architecture, which is Soar. And I tend to think it's breaking that boundary. You can't really see it, but it's sort of kind of breaking it. And there's me and my research. We'll get to that little thing at the end. So let's start off without further ado. AI has done some awesome things. And if you open up kind of a classic textbook from East 492 or something, you'll see amongst many, many other things, these kind of core strengths, things like reasoning, planning, and so forth. I thought I'd just dive into a couple examples of these real quick. So reasoning. One great example of this is the Psych Project. This is out in Austin. They have one of the largest knowledge bases kind of curated, over 500,000 concepts, 5 million facts, 1 million rules. They use a complex reasoner that does forward, backward inference, things you would learn about in intro AI courses. And they do some really, really cool applications with this. So things like anti-terrorism, cyber defense, disaster contingencies. And I thought I'd show you one kind of cool example of it. Absolutely impossible to read. That's okay. I'll get us there. So in addition to all this existing knowledge, they describe a computer network, and then they describe software and hardware vulnerabilities. So this is all in the system. And then they ask the question, how would you break into this network? And this is the explanation of the result. It actually produces an answer and say, how do you get there? And it does things like, I'll read it somehow. Hypothetical hacker sends an email message to a particular host, gets them to come to a website. And when they go to that website, there's a string there that overflows the memory buffer for Real Player version 7. Of course, this tells you how old this example is. So once it's overflowed, it installs a sniffer program, gets your password, logs into that computer, downloads something that exploits Windows NT, also tells you how old this is. And then once you've gotten that, you've gotten into the system account. So this is all off of core AI reasoning. And it seems pretty cool. Another core AI strength, extracting patterns, or we call it machine learning. One example of this is one that I like is AID. This is AI for Developing Regions. You can look at them, aid.org. They do some really cool things with machine learning. You can do predictions, so things like food shortages, post-disaster need, disease propagation. So they had some cell phone signaling stuff from a particular country, and while they were collecting the data, there happened to be an earthquake. And this has nothing to do with the recent travesty in Japan, but they were able to look at that and actually predict propagation of the need for clean water, having to do with known models for how disasters have gone in the past and where clean water need to be to prevent disease. They do distributed medical diagnosis. So if you don't have a whole lot of doctors in the region, you don't have a lot of equipment, and travel might be hard, how you can do that. Voice-based services for illiterate populations. And here's one example, not terribly easy to read, but imagine you want to screen people for heart conditions, and you don't have a lot of equipment around, and you don't have a lot of doctors. So you could train nurses or train people to go up to have screenings in remote villages and have a phone that uses its microphone to collect audio data about a person's heartbeat. And so this right here is actually data from an iPhone microphone. And so you're seeing the sound waves go through, and then throw a little machine learning on top where you can't see there's little pluses here where they were actually detecting when the heartbeats were going. And they could use this to then perhaps say, okay, you've got a problem, you should either go to this hospital, or maybe the doctor could come to you, or maybe they could diagnose some medication if it was something treatable. So another strength, games. So this kind of comes down to two basic categories here. So one is you have competitive players for games. We know about chess, so this was Deep Blue. So then we had Jonathan Schaefer had one of the competitive checker players and actually solved the game. And that means having a kind of perfect strategy for playing any given game. And to get a sense of size, this was 500 billion possible positions, or 5 times 10 to the 20 positions. He also dabbled in poker and was able to have a world competitive poker player. We all know about Watson, which recently showed that it was competitive with world-class Jeopardy players. And then as a whole another category here, game theory. So a couple weeks ago, I had Mike Wellman come in and talk about how analytical game theory could be applied to trading agents, and this is the logo from their group, but you could also look at markets, auctions, P2P, security, and so forth. So these are really, really great applications of AI, but they have typically some pretty strong assumptions. So that is, you have typically a single, well-defined task. You know what the inputs are, you know what the outputs are. Typically narrowing the type of data you're going to have to deal with, the amount of data, and the kinds and the amount of learning and adaptation it's going to have to go through. It also tends to be pretty short-term, seconds, minutes, hours. So given these assumptions, you can do pretty cool things. But let's start thinking about next-generation tasks. And before I show what my list is, this is the Student AI Lab. So imagine you guys have some ideas. Tomorrow, we're going to apply AI to some really cool things, and we have fantastic next-generation AI. What would you want it to do for you? What do you think are some really, really cool applications of next-generation AI? Fly aircraft. So right now we have teleoperation, right? You would say having some more intelligence in the cockpit, or perhaps having an individual being able to control multiple aircraft. Any others? This is AI Lab. You must dream about this stuff.
Self-controlling robotics to perform repairs in dangerous situations.
Repairs and very cool. Got one back there? Robots for urban warfare? Did you have one? No? Do research for you. Awesome. Okay, so this actually hits a lot of what I tend to think about. Okay, so kind of area of cognitive robotics. These are robots doing cognitively complex things. Things like long-term exploration, whether it's under the ice caps, going into dangerous places, going to Mars, where it's a 30-year mission. That'd be kind of cool. Search and rescue, going into places, into buildings, have dangerous circumstances, whether disaster, something like that. Synthetic teammates. I'll actually talk about, at the end of this, a military application of synthetic teammates. But you could also imagine medical helpers. They know something about the operation they have to perform, and they can actually assist the doctor, whether it's holding up somebody's leg so they can work inside them, or perhaps detecting there's a strange smell. Maybe you hit the wrong organ. I'm talking about things I know nothing about, but it's okay. Thought this was kind of cool. Do you remember Rosie from the Jetsons? So imagine Roomba for laundry. So you leave the home and it goes in and it picks up your laundry and it knows you're going to have a meeting the next day, or it knows you're going to have to give a presentation, and it cleans your shirt so it's no longer brown, it's white. Wouldn't that be cool? Personal assistants at the office, so helping schedule things for you. Tutors. So there's actually some AI work in this, which is say you're not getting a concept. The AI tries to figure out what's the state of your mind so then it can pose problems to you that will help get past your particular blockage. Scientific knowledge discovery. One of the number one answers from AI grad students was, have a program that makes my thesis for me so I don't have to. But imagine if instead of once every 3, 4, 5, 7 years, a student graduated from their PhD program and made a little dimple, we could have programs that did this automatically, and we could just grow the amount of knowledge exponentially. That'd be kind of cool. Resource management, sending food across the world, getting people transported correctly. My claim would be to get to these next generation tasks, we need something I'm calling human-level AI. And I'm going to try to talk about what I mean by this. These are agents that are autonomous. They have their own goals. They perceive the world. They take action in the world. They have their own knowledge. They can communicate with others. They're working on a long-term basis, so not minutes and hours, days, weeks, and years. They also need to be reactive to their environment. It can't just be, here's a problem, go away and think about it for 10 minutes and come back to me with an answer. You're responding to your environment, you're making good decisions, and you're always reactive to the changes that could take place. You need to be able to work on multiple tasks. And the picture down here is showing multitasking in the sense of doing everything all at once. What I mean is that the program is able to do multiple things at once. So the checkers player should also be able to do Sudoku, should also be able to schedule calendar appointments, and so forth. The kinds of tasks it's working on may not be pre-programmed into it. So right now, it takes a lot of time and effort to give knowledge and teach tasks to computers, and that takes the form of programming, laborious programming. Instead, this should be learning. So you have some initial knowledge, you gain new knowledge from interaction with the world, perhaps communicating with humans, communicating with other agents, learning new skills, and improving at skills. The types of tasks you're working on should include different kinds of perception and knowledge. So whereas right now, AI typically takes in a set of images or a video or maybe some text to do some natural language processing, you should be able to work across different kinds. So images, videos, text streams, and so forth. And finally, I think they need to be robust. So typically, AI systems right now try to optimize over some set of conditions. And when something changes about the problem or something changes about the environment, they tend to go down pretty hard. And we saw this in Watson, where it wasn't quite sure about this airport that's in the US and World War II history. That was all kind of crazy. So the answer ended up being the US city of Toronto. So needing to do better in the case of failure. By the way, if at any point you have questions or something, feel free to stop me. Just raise your hand and ask a question, especially if you disagree with me. So one approach to human-level AI is the research field of cognitive architecture. So the goal here is to develop and understand human-level intelligence across a diverse set of tasks and domains. A cognitive architecture itself is a specification of those aspects of cognition that are constant across the lifetime of the agent. And roughly speaking, you can think about nature versus nurture. Nature is the things that are going to serve you over a long period of time. You can optimize this over long periods of time, make it really fast, really well suited to your environment. And the nurture are the things that are going to change over your life, the knowledge you're going to obtain, and the adaptation you make on a day-to-day basis. So the kind of things that remain constant in these kinds of agents are going to be the memory systems that maintain the goals, beliefs, and experience that it goes through, the kinds of representations of knowledge over time, the processes that would take this knowledge and process over to lead to behavior, as well as learning mechanisms in order to learn new knowledge. Now, to ground this out, I'm going to show you what a prototypical cognitive architecture looks like. And we get two box diagrams. So we have some form of perception. This is how information is getting from the environment to the agent. And this could take multiple forms. It could be audition, it could be vision, it could be text streams. And these are typically represented in some sort of short-term memory. And it's capturing things like what the agent's doing, who's around it, where it is, its short-term goals, and so forth. It typically has some long-term what's called procedural memory, or the knowledge of when and how to perform actions. So when this knowledge is applied to the current situation, the agent can then select an action to perform. And typically, it also has some sort of learning mechanism that can take the current situation, take the actions that it performed, and feedback, and learn either new knowledge, new skills, or improve its skills about existing actions that it knows how to perform. You typically have also a declarative long-term memory. These are facts about the world, such as addition facts, history, geography, but it can also be kind of personal experience that the agent has in the world, such as its first robotic kiss, which would be very cute to remember. And also, it'll have some sort of mechanism to learn these facts as it experiences the world. And so when perception comes in and it's represented in the short-term memory and all this long-term memory gets applied, selects an action, and this will turn into action actually in the world, such as running around or writing something. And so what typically happens is you have a cycle. So perception will come in. There will be some search over knowledge about what I could possibly do in this situation. A decision is made about what to do. Knowledge is then applied towards the decision, which could incorporate action in the world, which then could cause perception to change, and you start going in this circle. So given an architecture like this, an agent becomes a combination of two things: a fixed architecture and dynamic knowledge. And I say fixed. This is fixed in the sense that the source code that runs behind it is fixed. It's kind of compiled in. But these could be adaptive processes, such as learning mechanisms that are going to add things to the system. And knowledge is gained over time through these learning mechanisms.
To what extent does this model mimic how humans actually perform?
So I was actually going to talk about this in one slide. Can I go through the next one? And then if I don't answer your question, raise your hand and hold me to it. Cool? OK, so architectures like this are typically applied for different reasons. And they typically fall into about three categories. The first is the idea of biological plausibility. That is, we know that human intelligence arises from connections of neurons. So there's people, such as in the Libra project, that say if we can understand at a really low level how neurons operate and how they connect, then maybe we can start to understand human intelligence. And if we can model this in the computer, maybe we can understand better how neurons in the human brain work. There's a level above that, which is looking at psychological plausibility at the level of the mind, brain areas. And the idea there, again, is if we can model in a computer what we think we understand about the human brain in one of these architectures, maybe we can make predictions about what humans would do in a particular situation, or actually explain data that humans have performed on a task. And the most common architecture that does this is called ACT-R. This is out at Carnegie Mellon. John Anderson, Christian LeBaer are heading up this project. It's been used for hundreds of what are called cognitive models. These are human performed a task. We think we know what's in the human's mind when they were performing that task. So we put that into our system in terms of the knowledge. We ran it on the same sort of task, and we got a graph out saying this is how fast it performed, this is what it chose to do, and it matches human data. Another platform is actually called EPIC. This was developed by Dave Kiris and Dave Myers right here at the University of Michigan. Dave Myers is down in psychology. Dave Kiris is actually in the interactive systems group. He teaches the advanced C++ class. So the third kind of grouping of cognitive architectures looks at agent functionality. And that is, we could be inspired by how humans work. We can learn from that. But what we really want to do is have really, really cool agents that are doing cool things. And maybe this isn't how humans work, but we're going to go for it and we're going to try things out. And for the rest of the time, I'm going to focus on one of these, which is called Soar. Did I answer your question? Cool. All right. So the Soar cognitive architecture. See, we're progressing into the state of the art up here. It was created in 1982 by three gentlemen. I'm going to introduce them one by one. First is John Laird. This is my advisor. He's a professor up in AI. At the time, he was a graduate student at Carnegie Mellon. Now he teaches the games course, I think recently the professionalism course. His advisor at the time was Alan Newell, who is one of the founders of AI and has done amazing things in the field. Unfortunately, he passed away in the early 90s. Another one of his graduate students was Paul Rosenblum. And Paul Rosenblum actually came up with chunking I'll mention this later, but it was the first learning mechanism in Soar. He's currently a professor at the University of Southern California. He's trying to apply knowledge about graphical models to build uniform substrates for new cognitive architectures. He also has connections with ICT that has a virtual human project, and I'll show examples of that later. So before I show what Soar is and what it can do, just some distinctive characteristics to separate out from the rest of the crowd. It efficiently brings to bear large amounts of knowledge. So typical systems like this in a research setting are applied to very, very small problems, small amounts of knowledge, and tend to blow up when you go beyond kind of set boundaries. I'll be giving an example of this later. It has diverse mechanisms that support general problem-solving methods, and this speaks to its ability to be applied across a lot of different tasks. I'll be showing that in a minute. And it's also publicly distributed and documented, which is another rare case. You read research papers, and you see a lot of these box diagrams, but you can never actually play with it. And this is something that's freely downloadable. You can get to the source code, runs on major operating systems, and you can actually connect to it with a lot of different languages and connect it to a bunch of different systems. So I'd show you what some of these systems have been and are today. So going back a long way, you go to Dell or Apple right now and you want to configure your computer. You have a whole bunch of options and you just click some lists and you think this is really easy. Back in the day, before things were nearly as standardized, this was actually really, really complex. There were a lot of constraints. You were basically saying, I want you to build these things for me. And Soar back then was applied to this task. This is computer configuration. And after that, there were things like natural language processing, modeling human-computer interaction. And then I mentioned the virtual human project at ICT. This is having avatars that could do things like welcome you to the University of Michigan and answer your questions about it, or maybe help soldiers in understanding the culture of a country they haven't been to and a culture they haven't been to. Other sort of systems. A really, really important one was TAC Air Soar. This was the largest rule-based system. It was used to fly training missions for Air Force pilots, had over 8,000 rules, and actually ran for 48 hours of continuous real time. Another interesting one, QuakeBot. So it was playing the game of Quake, and it actually had a model of other players. So as it was going around trying to play the game, it actually was modeling other players and predicting what their actions would be and changing its own actions to adapt to that. So the mount bot, so something here says unpredictable behavior. Like, wait, do I want unpredictable behavior? There's certain instances where this is actually pretty important. Training is one. There have been instances in training personnel, specifically military personnel, where if there's predictabilities in your system, the individuals will actually adapt themselves to what's predictable about the training as opposed to the task. So you can actually generate novel behavior using this. Splinterbot was an interesting one. So Edwin Olson is a professor upstairs. He just came back from Australia where they won an international robotics competition. And the kind of robots they were using, this was an earlier version of it, but they were Splinterbots. And so we actually have Soar running both on simulations of this as well as actual hardware. And John Laird right now is in Utah talking about systems where Soar is running for hours around things like the third floor of the computer science building, collecting things, going to different offices, and planning around it. Some really, really recent applications. So a couple years ago, student graduated. Part of his thesis was he got an Atari emulator. And he just threw a really, really easy, quick vision system at it so it could identify things like fish and frogs. And using reinforcement learning in Soar was able to make players that could actually improve performance and play pretty well at these whole different set of games. Current student named Shivali Mohan has applied Soar to play the Infinite Mario game. So this is SNES Super Mario, except you just get to the end of the level and you start all over again. This was used in an RL competition. She was able to make agents that played pretty well as compared to their agents. Recently, I put Soar on the iOS platform. We actually have it also running on Android devices, but I'll talk about iOS. A couple applications here. Imagine you go to the App Store and you find a game and you download it. And it's something like tic-tac-toe, which is shown here. And it starts off playing really, really poorly. And you're like, oh, I'm beating it, I'm beating it. But as you're playing with it, it's actually accumulating experience from playing with you and adapts to you. So it's not like you go to a game and you say, I want to play against the easy AI or the medium one or the high. It actually adapts to you and it gets better according to its play with you. And so everybody's game is actually individually personalized. So we made a prototype of that. Also worked with Georg Essel upstairs to have novel music being played from iPads after interacting with individuals. And we also I got it playing a web-based game. It's a dice game, so probabilistic learning. So it can interact in a lot of hardware and software environments. And you can do this and connect it to your own systems. All right, so what does Soar look like? I'm going to try to put up a diagram that looks something like what I put up earlier in terms of the prototype. So lots more box diagrams. So we start off with the part that looks pretty much like what the prototype looks like, which is short-term memory. To ground this out a little bit, in Soar, this is actually a directed connected graph. But again, it's maintaining things like current situation, where it is, short-term goals. We then have setting off to the side a decision procedure. This is very much like what I showed earlier in terms of choosing actions, but these could be internal actions, things like look something up in memory, as well as external actions like drive down and find a particular office. It also has arbitrary form of perception as well as action, but we also throw something in between perception, action, and the short-term memory, which is spatial and visual processing. And this allows it to interact with continuous domains, such as something like Atari or in a robotics platform. So it has procedural knowledge. Again, this is knowledge of when and how to perform actions. And it has a couple different learning mechanisms. So one is called chunking, and this is learning new skills based upon knowledge it learned from kind of solving subtasks. It's like, I had to think about this before, but I knew what kind of the inputs were, I knew what the outputs were. I'm going to combine this together, and now I know how to perform a task faster. There's also a reinforcement learning component to it, and this is learning how to optimize towards a reward signal based upon feedback from the environment. Turns out that sometimes we get gold stars from acting in the environment, but sometimes we need our own intrinsic kind of reasons for performing tasks. So a graduate student a few years ago looked at emotion modeling, and so we're using something called appraisal theory. So based upon the current situation, it would generate emotions. These emotions would then become the reward signal, and so you would actually learn how to perform actions over time given no kind of external reward. It also has two long-term memory systems. So one we call semantic, and these are facts, general facts about the world, independent of the context in which they were originally learned. And then we have an episodic memory, which is memory of experiences as they happened. And so these interact with the short-term memory, and there's learning components with them. And we are going to focus on this from here on out because it turns out this is what I do. So we get to focus in on the little dimple that I think is important out here. So my research, exploring and evaluating long-term declarative memory systems that are effective and efficient across a variety of tasks. So at this point, we have some sense of what declarative memory systems are, and we've seen a bunch of different tasks, and the question are these underlined words. What does effective mean, and what does efficient mean? That's what I'm going to focus on from here on. Except I don't really know what effective means, but we're going to try to build up an intuition for that. So I'll have a little space here. Graduate students love to make spaces of things. One axis is going to be capabilities, the capability to remember and what you can do by remembering things. And the other is going to be this thing I don't really know all that much about, which is effectiveness. So I'm going to put points in this space. We're going to try to understand what it means to be effective at tasks and connect that with the capability of remembering. And a lot of this is going to draw on Hollywood to inform our intuition. So we'll start off down here with a movie called Memento. So I'll be playing a clip in just a minute just to give you an idea. The individual who's shown had a dramatic occurrence. He was kind of knocked out. Burglar came in, killed him and his wife. Killed his wife, didn't kill him. And now he's woken up. He can't make new memories, but he's trying to figure out who killed his wife. So let's take that and...
Oh, wait. Where am I? Some anonymous motel room.
I guess I've already told you about my condition. Oh, well, only every time I see you.
It's my memory.
Amnesia.
No. It's different from that. I have no short-term memory. I know who I am. I know all about myself. Since my injury, I can't make new memories. Everything fades. I've told you this before, haven't I?
Okay. So he has some sense of who he is. He knows what his goals are, but he's having trouble making new memories. So he tries to get around this. Things like you saw, he tattoos himself with really, really important stuff. He also carries around photographs. He writes notes to himself. So that gives him some capability to remember. But people can still kind of take advantage of this. So you saw the guy at the hotel, can charge him extra, charge him more often. Kind of the person playing his friend could walk away from the situation, let the guy forget, walk back, and then pretend the situation never occurred. So in terms of effectiveness, he was actually a cop, so he's able to make some progress, and I won't ruin the movie entirely for you, but some hardships, and a lot of it has to do with the difference between him and anybody in this room, aside from being a cop, is he can't make new memories. So let's look on the other side of this. Let's take an instance of a person who can remember lots of things, even probably more than anybody in this room, but still has a problem with effectiveness, and this is from the movie Rain Man. Before I show the clip, it's actually inspired by an individual by the name of Kim Peek, an American savant. He has a photographic or eidetic memory, but also has some developmental disabilities. In the movie, this is shown as being autistic. So what we're going to see here is a clip from the movie. So here, Dustin Hoffman is playing this individual. Tom Cruise is his brother. Their goal, or Tom Cruise's goal, is to get to California from this airport. And Dustin Hoffman can remember lots and lots of things about airplanes, and we'll see how this works towards the effectiveness of getting to California.
Because there's an airplane out there.
Yeah, that's right, and everybody's boarding. Let's go.
Airline travel is very dangerous.
But don't be silly. It's the safest travel in the world. You're going to love this. Trust me.
Yeah.
Now, come on.
Oh, no.
Ray,
Yeah.
we're in an airport. People fly out of airports. What do you think we were doing here this whole time?
Yeah, flying's very dangerous. 1987, there were 30 airline accidents, 211 were fatalities, and 231 were death passengers.
Well, this plane is very safe. Believe
Yeah.
me. Now, I got to get to LA, and I don't have time for this shit.
Yeah.
Come on.
Oh, I
Ray,
don't know.
Ray?
I don't know.
You don't know?
No.
What, is
I
it
don't
this
know.
airline?
Yeah.
Is it this airline?
Yeah.
Okay, fine. We can, there's an American plane.
American Flight 625 crashed April 27th, 1976.
We don't have to take American. There's a lot of flights.
Yeah, take another airline.
Continental. We'll take the Continental.
Continental crashed November 15, 1987. Flight 1713, 28 casualties.
This is very serious, Ray.
Yeah, very serious.
You see, I have to get to Los Angeles, right? So you're gonna get on that plane. Do you understand me?
Yeah.
You're gonna have to get on a plane.
Yeah, get on a plane.
Yeah. Now there's a Delta.
Yeah.
Delta, I mean, it leaves at midnight, Ray, you know, but Delta, how's Delta?
The Delta crashed August 2nd, 1985, Lockheed L-1011, Dallas, Fort
All right,
Worth.
great.
Terrible wind chill.
All airlines.
135
All
passengers.
airlines
30 crashed.
have crashed at one time or another. That doesn't mean that they are not safe.
Qantas.
Qantas?
Qantas never crashed.
Qantas?
Never crashed.
Well, that's...
Never crashed.
I mean, that's going to do me a lot of good, Ray.
Yeah.
You see, Qantas doesn't fly to L.A. out of Cincinnati. You have got to get to Melbourne.
Australia.
Melbourne, Australia, in order to get the plane that flies to Los Angeles. Do you hear me?
Canberra's a capital.
Let's
16.2
go.
million population. Six very
Don't
lovely
give me a hard
beaches.
time. You and I are going to get on this fucking plane.
No, no.
We're not going to take the plane. He's okay. He's okay. He's okay. We're not going to take the plane. Just relax. He was upset. We were going to take the plane. We're not going to take the plane now. We're not going to take the plane, Ray. We're not going to fly. Okay?
No flying.
All right. So the character is able to remember lots and lots of facts. These do not work out in favor of accomplishing the task. And this is both in terms of social awkwardness, screaming in the airport, probably not the best thing to do, but as well as just getting to California, and they have lots of adventures from here on. But the point being, great capabilities in terms of memory. This doesn't make for effectiveness. All right, so let's try to move into an effective space. And this is actually a real individual. He's the fourth person who's diagnosed with what's called superior autobiographical memory. This is an instance of a real individual. He's 58, lives in LA. He works as producer for the Tennis Channel. So let's just see a little bit of this.
Lots of sports fans can remember highlights from particularly exciting games. Bob Petrella, a Pittsburgh Steelers fan, remembers every game.
When was the last time the Redskins beat the Steelers?
Let's see, they played them in 2004, and the Steelers won. They played them in 2000, the Steelers...
We sat there as he scanned back through 19 seasons in 19 seconds.
Oh, in 91. Yeah, they played in 91, November 17th, 1991. This is fun.
Bravo.
We tried even further back.
What were the last 2 games in October of 1979?
Let's see, the 22nd, they played Denver on Monday night, and I think they won 42-7.
Yep.
And then they played, Dallas on October 28th, Sunday. It was on CBS, so you can get that game.
Pittsburgh, Pennsylvania.
We did. We got that game. And 31 years later, he was able to describe plays.
Staubach was scrambling, and Elsie Greenwood just slammed right into him. It was in the fourth quarter.
Staubach really took a shot. He was hit by Greenwood.
He even remembered specific images from the broadcast.
I remember Staubach just sitting on the bench. You could just tell he was out of it.
How about November 11th, 1990?
They didn't play. That was a bye.
You're good. That was a trick question.
No, I remember that day because I was depressed. I had broken up with this woman, and I was going out to run a couple of videos, and I was thinking about it.
All right. So they show other examples. This is a great, it's about 60 minutes to watch. Show examples of people remembering all sorts of things. It's not just limited to sports facts. It just happens to be that he's a sports fan. He's watched a lot of sports, and these are the memories that he has. And lives a perfectly good life, very effective across a lot of tasks as humans tend to be. So let's try to push a little bit beyond what we think humans can do in terms of effectiveness, and we'll go back to Hollywood. This is a brand new movie, may not have heard of it. The core concept, you use some percentage of your brain right now. What if you could take a pill that would let you use all of your brain? So the character is going to use memories of watching movies and watching documentaries to actually learn a new skill on the spot as it's needed.
A fight? Don't know how to fight. Or do I?
So lots and lots of memory capabilities and really, really high on the effectiveness scale. So we have a sense of this space, and I'd like Soar to be right up here. Lots and lots of capabilities, really, really effective. Let me be a little more precise what I mean in some of these capabilities. So these are capabilities that you get because you have the ability to remember things and you wouldn't have otherwise, and can be applied across a number of tasks. So one example of this that's been researched a little bit is virtual sensing. This is expanding your sensing beyond the immediate situation back to details of past situations. So let me get a set of hands. How many people here have cars? Okay, so a little over half. How many people using their immediate senses, meaning can you see, hear, touch their car right now? Somebody tell me the color of their car. We got silver. Red? Nobody can see it, but you can tell me a detail about it. If you go to the mall and you park your car and you go inside, assuming you can remember it, you can find your way back to your car. So your immediate senses can't do anything, but the fact that you have memory allows you to do things like answer questions about it or perform tasks like get back to your car to go back home to bring your groceries home or something like that. So it's a capability that can apply across a large variety of tasks, and it's there because you have the ability to remember past situations. Another example is called action modeling, and this is your ability to predict the consequences of future actions based upon your experience in similar situations, possibly with that action in possibly different circumstances. And we saw the Hollywood version of this, which was I watch Bruce Lee fight, and so I will predict what I'll be able to do against people in the subway. All right, so this gives a sense of what effectiveness means, at least a fuzzy, hand-wavy sort of sense of this. Let's look at efficiency, and this is actually my only graph. I was holding back as a grad student. I want to put graphs in front of you, but this is my only graph. So what this is, this was a project done by the Air Force. They wanted to come up with a synthetic teammate for Air Force pilots, and they wanted the pilots to be able to interact with the synthetic teammates using natural language. So they said, okay, let's get a cognitive architecture. They used ACT-R in this case because it's cognitively plausible. And they said, okay, in order to have natural language capability, we're going to fill it up with lots of linguistic knowledge. And they use a data set called WordNet. It's made out at Princeton. It's essentially a really good dictionary and thesaurus and has sources of other knowledge. And they started putting it into the system, and they started measuring how long it would take to get information out of it given a particular cue, like what's the meaning of the word to run, the verb to run. So on the y-axis here, we have retrieval time expressed in milliseconds. On the x-axis, these different groupings are how much knowledge is being placed in the system in terms of how many items out of this knowledge base. So WordNet has about 820,000 pieces of information about linguistics in it. We have 1,000 pieces, 5,000, 10,000, 20, 80, and 240,000. So we're getting up to about a third of the knowledge. The dark gray here was ACT-R. Out of the box, you download it, and you start trying to put WordNet into the system. So as you put more and more knowledge, the amount of time to answer any given question was exploding. And actually, when they tried to get a third of the information into it, the system just crashed. It could not handle it. So that is to say, just because you have the capability to remember, and you have a system that can support it, when you start putting knowledge into it, if it starts negatively affecting your performance, this is a really, really bad thing. So the Air Force researchers developed the light gray system. And the basic idea behind the approach was they took a relational database system called Postgres, and they just attached it onto the side of ACT-R's head. And so they loaded WordNet into Postgres, and they said, hey, look, we can query no matter how much knowledge is in the system, and it takes between 40 and 50 milliseconds. And this happens to be the amount of time as required for reactivity, typically for humans. This is about the decision cycle time for humans. So said, this is a good start. So let's try to make an efficient implementation. And so this was put into the semantic memory system of Soar. We were looking at novel data structures and algorithms, but building off of existing work. And I'm going to talk about each one of these and point you to the class where you could learn more about it. So an inverted index is a way, if you have a whole bunch of objects and each of these objects has features, of searching and finding an object based upon a feature. The most common use of this that you would know about is in web search engines. So the objects in this case are web pages. The features are, for instance, the terms in the web pages. So when you go to Google and you type in memory, it's going to find you the web pages that have memory in it. And all of them use inverted indexes. It's a really, really efficient way of solving this problem. If you took EECS 485, this is web database systems, you would learn more about this. So we applied partially that. Statistical query optimization. This is, as you're loading knowledge into the system, if you can keep some statistics about it, when a question comes at you, you can try to formulate your search through the knowledge base better based upon information about this. This is used in all relational database systems. So for instance, if I had a query about blue zebras, in your life, you've probably seen a lot of blue things in your life. You've probably seen few, if any, zebras. So based upon your knowledge, let's look at the zebra things first. There's going to be very few of those, and we'll see if any of them are blue. The reverse of this being, let's think about all the blue things and see how many of them are zebras. You could see how those would be very different in runtime. So if you took 44 or even 584, you'd learn more about this as the database course. And then we also apply, was there a question?
So this is kind of like what Watson got wrong with that Final Jeopardy.
So these are ways to make things fast. So the question was about Watson getting the question wrong in terms of getting the Canadian city instead of a US city. So these are ways to make things fast. Watson got it wrong because it, for instance, could find candidate answers in the wrong way. So Toronto is a city, but it's not a US city. And
there are Toronto cities. There are cities named Toronto in the US, but none of them have 2 airports.
Is it 2 airports? Okay. So there's a question as to how it was coming up with its answers, whether or not it was using inverted indexes, statistical query optimization. Again, these are ways to make things faster while still getting correct answers. Heuristic search is something, a basic method in AI used in a lot of different ways. In this case is, how far do you have to search in your knowledge base before you know you have the best answer? So we applied a combination of these. We threw on additional components that were novel. And let me just talk about some of the results we got. In terms of the data we showed on the previous slide, that got out to 240,000 pieces of information. We went the full 820, so 3 times more data. And we're able to get 100 times faster queries on this. This is in Soar right now that you can download, but it could be applied across numerous systems. This same system was stable and efficient for real-world tasks on robotics, as I was describing on Edwin's robots, as well as mobile music domains. And now we're looking at extending this to incorporate biases that could be useful. So for instance, if you get a question, it can have multiple different answers, like a city that has a particular airport. How do you make a decision based upon having no additional information? And it turns out that humans actually have some strategies for doing this. For instance, if you were recently talking about a mayoral race, that may get you to Chicago faster. And so the future work I'm planning on doing on this, you're looking at adding additional capabilities to the system that could be used across these different tasks. So all the work I put in on the side of extending these memories will make all the applications that you use across different domains a whole lot better. These would be general, adding to problem solving in a lot of different problems. And then evaluating that on more tasks and data so that agents that are made on this, you can understand how they're going to perform and across different tasks and have lots of good data on that. So Soar is really, really awesome, or at least I think so. If you wanted to get involved and use Soar, you can go and download it right now. So we have a Google code site. There are binaries there that are available on multiple platforms. The source code is available. We're actually working on a release, hopefully new one in early April. There's extensive manual, lots of tutorials to get you started, and we have an email list. If you have questions, you can email it, or you can come upstairs to our graduate student group and ask us questions. If you're interested in getting some more reading, Unified Theories of Cognition was written by Alan Newell based upon some lectures he gave of that same title. And this gives you kind of a background from a psychological perspective on the research area that is cognitive architecture. Also on our website, we post most of our publications by the Soar group, so you can see what we're doing these days. Also, on an annual basis, we have a Soar workshop, and you can get more info at this site. We hold tutorials on Soar. There's talks. People from around the country as well as around the world come to this to talk about how they're using Soar, and we also talk about the improvements we're making on the back end of Soar. So that's all I have. Thank you very much. Do you have any questions? No questions at all? So we all agree Soar is the greatest thing since sliced bread? Cool. Thank you so much.